Good morning, everybody. Any questions before we start? Was everyone able to get their MCMC to converge? I think I saw just about everybody's. So what I want to do with that is, Morgan, when you get a chance, can you fit that to the real data? And then we can talk about the output and interpretation, and then what that means for writing up your results and discussing those results in terms of a thesis or dissertation or publication. And then we'll also talk about adding some, once we see those results, maybe Monday, we'll talk about adding some complexity to deal with some of those idiosyncrasies you were mentioning when you were talking about the data, like you have multiple response variables, multiple predictor variables, and how we can deal with those types of questions. And then also this analysis is part of a larger analysis that's your thesis. So this is one component of it, and how we can maybe use this information to integrate that into your larger analysis. So from your description, your overall objective is you have this huge archive of feathers related to mercury, but you don't know the relationship between the feathers, which are data that are easy to collect, and organ muscle tissue, which are harder to collect, require sacrificing the animal. And what is really important might be the muscle tissue. I mean, that's where the results of the mercury might actually manifest in the birds. So how do we integrate this relationship of a smaller subset of data into this larger analysis? And we can talk about that. There's a couple things just off the top of my head. We could, from our relationship between organ tissue and feather tissue that we've looked at, these 39 samples, we can develop a distribution that describes the relationship, and then we can use that distribution as a prior distribution for our larger analysis. I think that would probably be a good place to start. Okay. So last week we looked at an application. Last couple of weeks we've looked at applications. We've looked at Morgan's application of counting seedlings in 4 different treatment levels and how we deal with, let's see, that wasn't the multiple intercept model. Did we fit the multiple intercept model for your data, Morgan? I mean, Bryant? We fit just a generalized linear regression model with a bunch of different covariates. Yep. Okay, but then after that, we talked about fitting multiple intercept models. And the next extension to that, the next level of complexity in our hierarchical modeling is to account for not only multiple intercepts, but multiple slopes between the response variable and the different level of grouping on the predictor variable. And for that, I think we have a nice application to go over. And Kelly is going to talk about some of her research that she's planned. And this gives us a nice example to extend the complexity of our models and how we might do that. So Kelly, did you want to talk about your data a little bit?
Yeah, I can do that.
Yeah.
Awesome. Do you want me to maybe show anything too?
If you have anything to show, yeah, that'd be great.
Yeah, sweet. I'll go ahead and show our screen. But essentially, I have multiple, I'm pulling data from multiple USGS stream gauges around the east and west side of the Lake Tahoe Basin, trying to get a sense of nutrient dynamics in these streams over time and how they potentially function across a precipitation gradient. Sorry, this is probably going to take a second to not be so blurry. But essentially, so I originally, Perry, I think I said 9 sites, but in playing around a little bit more with the data, 2 of the sites are just super data poor. So I've removed those and I'm just sticking with these 7. So this plot is just showing values for total nitrogen in stream samples collected at one point at a stream gauge by month number, because there's over 20 years worth of data, but this is a federal science sampling campaign. So they normally just go out like 1 to 2, 3 times a year, if that, at these sites. So not fully sure what the most appropriate temporal resolution is to look at the historic data. For my own research moving forward, I'm going to be going out and collecting biweekly samples from these sites. So I'd like to have some sort of idea of how to handle like different temporal resolutions in the Bayesian framework that could be a lot closer than just that like more sporadic federal sampling campaign that you see here. So all of these sites, they're a little bit different in the watershed size, the watershed area, but I tried to get a fair amount of pairing on both the east and west shores. As you guys all probably know, the east side is much drier, gets a lot less snow, versus the west side is a much more precipitation heavy environment. So I'll just go ahead and throw this plot up of precipitation too. And apologies if that takes a second to load. It's probably because I cleared my environment before this, which was really, really silly. So sorry about that, guys. I'll just hold off on that for now then. But yeah, so interested in these nutrient dynamics over time, as much as we can predict them as a function of stream flow, essentially, which is somewhat deterministic on snowfall as a process.
So when you say precipitation gradient, most of the precipitation is in terms of snowfall.
Yeah.
That's what your measurements occur in. Okay.
Yeah, and the easiest and safest parameter to use for snowfall is either snow water equivalent, which is taken more at an incident level, or actually total precipitation accumulated throughout the season, which is a tiny bit frustrating because SNOWTEL is really not accurate in the way that they measure hourly snow so they pretty much just have a daily total, and they don't reset their daily totals within the way that it's collected. So it's a great data stream because there are a lot of SNOWTEL sites everywhere, but it's a little bit of a funky variable to actually dig into.
Okay, cool. Thank you for that, Kelly. So we have, let's go through some of these things you pointed out. That was a lot of information in a short amount of time.
Oh, sorry.
No, it's fine. You have 7 sites. At each of these sites, you have a response variable and a predictor variable, or at least one predictor variable, but it sounds like probably more. What do you think is? You have some notes here. Model statement.
Yeah.
Maybe do you want us to go through that model statement and what you were thinking off the bat?
Yeah, this is something that we talked about really briefly the other day, but we're thinking that, this overarching statistical statement could be something like nutrient concentration, which is here represented as like total nitrogen at site I during whatever temporal range we think is appropriate, whether that be like total for year or if we want to break it up by like month per year, is deterministic is reliant on this process mu, which could have these different beta parameters. As we kind of left it just originally when we talked as a slope and intercept, but we thought that we could use something like beta 2 also for season. This is where my lack of statistical background starts to kick in, Perry. So I'm really sorry. I'm not super aware of like functionally what these betas should be best in this system, but I envision them being something like, stream flow and precipitation amounts definitely would be things that I'd like to have in them offhand, as well as a seasonal component. And then we'd have priors that we decided would likely be normally distributed, as well as the sigma, which would be inverse gamma. We kind of thought it might make sense to do log normal, as all of these values should be positive real numbers. So we're looking at nutrient concentrations, which should be always above 0, as well as precipitation, which should be always above 0 and can be any range of number. And stream flow, same thing.
Okay, so we have nitrogen concentration in some units. Our data Y at site I during some time T. Those come from log normal distribution that has some mean associated with it. And this mean, we're getting used to using the log normal a little bit more, especially after last week. This is going to be on the log scale, so this mu can be either negative or positive, even though our y's are only positive. So we have mu. I realize you can't see this, but what I'm writing, but you can still see what Kelly has up here, which I think is probably more important. Mu I at site T. So we're going to have a different mean at each site and each time period. And then we have some uncertainty associated with our data collection process. If we collect 2 samples at a site during any time, those might be slightly different. And those differences are controlled by that sigma squared. So that's our data model. And then we have this process model of mu. So you said your unfamiliarity with the statistics. This is more of the mathematics, the mathematical modeling on mu, the deterministic modeling. And we have a linear equation. It's linear because it's beta 0 plus beta 1 times something plus beta 2 times something, plus however many betas you want to put in. It's that linear form where you have beta 0 plus beta 1 times something plus beta 2 times something. Okay. So we have mu it equals beta 0 plus beta 1. And you said the probably most important one in there is stream flow, right? That's kind of the center of your question. Okay, so I'll say x1 and x1 is stream flow. All right, now I do want to share my screen for this.
Yeah, no, I'm happy to stop.
I can just override you. Okay. So here's where we're at right here. We're developing a mathematical relationship between the expected nitrogen relationship, mu, the expected value of y, and some of our predictors that we're interested in. We said x1 was stream flow. We're going to have different stream flow at each site during each time. So we have subscripts I and T on there. Now, when we're developing this mathematical equation here, this can be the easiest place to start is a linear equation. That's something that we've seen before in research and reading and in introductory stats courses, this beta 0 plus beta 1 times something, this linear equation, right? But it doesn't have to be linear. And this is where we can start to incorporate some of the complexities of the ecological system in here. And this is a great place to start. This is what we should be doing exactly. But I'm just thinking in moving forward, and maybe some of your other questions that you're interested in ecology, that if there's some developed literature out there that describes how nitrogen should physically be related to stream flow, and it's in the form of a deterministic deterministic function, we can include any type of function we want in here, linear or nonlinear. So one thing that I deal with a lot in population dynamics is how populations change through time. And let me just change the color here so I can erase this when I'm done. One thing that we have is population size at time t often equals, we think it equals population size at time t minus 1 plus what the population was at time t minus 1 plus some function for saturation. And this is often things like logistic growth model. What is that, 1 plus k over? We have r in here somewhere. R times n times 1 plus k over, what is the logistic growth equation? Let me just pull this up quickly. Okay, there's lots of different forms of it. And just to show the nonlinearities, I'll use this form because this looks very nonlinear. x minus x0, where x is some intrinsic growth rate, x0 is the value of the curve at the midpoint. Anyway, the point here is we can have some very nonlinear processes described in our process model. The easiest place to start is with a linear equation like we're doing right now. And that's really one of the nice things about Bayesian inferences. No matter how nonlinear our process model is, we can still estimate the parameters in those models. And that's where we can really start to combine ecological theory with uncertainty. So theoretical ecology is the study of developing these mathematical relationships between how process evolve. Things like how many animals are expected to be on an island given how far that island is away from the next island and how big that island is. Island biogeography, there's these mathematical functions that describe those relationships. And predator-prey dynamics, like Kolmogorov-Smirnov equations that describe the dynamics between snowshoe hares and rabbits in Canada. And all these other mathematical equations that have been developed in the field of theoretical ecology, we can incorporate those in our process here. And if there happens to be, and Kelly, you would know more about this than I would, if there happens to be mathematical equations that are describing how that relationship should look like, we can do some research and try and develop those here. Then we can estimate the parameters with our data, describe that uncertainty in that relationship, and then make inference based on those equations and that uncertainty. How well do those functions actually result in predicting the data that we observe? So I just wanted to be sure and put a reminder about that point in our modeling. All right, so let's go back to this process model here. It's a great place to start. We have a linear equation. We have some overall average, beta 0, and then we have how our expected value, mu, changes based on stream flow, and then Kelly mentioned seasonality. So we could do beta. So seasonality now is, you could do it as a continuous time frame, or you could do it as 4 discrete seasons. Because of the non-linear nature of seasonality, it's more of like a sinusoidal relationship. We could treat these as factors where we have beta 2 times season 2 plus beta 3 times season 3 plus beta 4 times season 4. And that way it'll allow the expected value of each season to be different from each other season, and you're gonna have 4 discrete groups. Or you could think about some other functions that allow it to move, something like, let's see. Plus beta 2 times the sine of the season, where season is 1, 2, 3, 4. Now we're treating that as continuous. Now we're not going to go into developing this function here because we have to look at the properties of the sine function, which we could do. And it'll give us that oscillating relationship as we go through the seasons. But let's stick with, for now, for this example, before we start thinking about the complexity, let's look at the relationship between streamflow only. So we have beta 0, beta 1. But now we realize there are 7 sites. And like we did with our previous example, what was the example that I used? It was biodiversity in treatment groups at Cedar Creek, if that was a good one. All right. Anyway, we had different intercepts for each group, but now we're going to talk about different slopes for each group. Okay. All right, so that's our process. We're going to have, if we draw this out, what it's going to look like, our deterministic function, we're going to have stream flow on the x-axis, and then mu on the y-axis, and mu is our expected nitrogen concentration on the log scale. And by expected, I mean the average. So in the end, what we're going to have is 7 different intercepts, one for each J. And last week, we talked about keeping the slope constant for each group, where regardless of what the intercept was, the slope was always the same. So we didn't have different slopes for our groups. So this was what our model looked like. But now we're going to add some more flexibility and say, what if we have a different slope for each group? So we have different intercepts and different slopes. And underneath these different slopes and different intercepts, there's an overall average. So if we think about these intercepts, it looks like the average of all the intercepts is right about here. And if we look at all the different slopes, we have about 4 or 5 that are positive and 2 that look maybe negative. So maybe we have like an overall average slope that looks something like this that describes everything in general. What we're going to be trying to do is figure out what the distribution of the intercepts are and what the distribution of the slopes are. Before we go on to finishing writing the model statement, are there any questions about this? What do you think, James? You have any questions?
No, I think I'm following it pretty good.
Okay. Ryan, you look like you're processing this a little bit.
I have a question, Perry.
Yeah, go ahead.
I know we're like letting seasonality lie right now, but if seasonality was to be a fixed effect on this predicted line, would it even fit into this plot? Because this is just expected end and stream flow. So would we like analyze this separate from stream flow? And because we're not, yeah.
Yeah, good question. Yeah. So what it's going to do in terms of the graphics of here, how it would affect this example is it's going to add another dimension. It's going to add an extra axis to this plot where if, let's say, seasonality is continuous, that's the easiest way to think about it conceptually. I mean, in terms of this graph, graphically. Now, each one of these lines is going to become a plane. So the plane is going to change depending on how flexible we are with our model. So if we just have seasonality and we have that as continuous in there, we're going to get this surface here that converts from a line to a plane that goes through all of our support of seasonality. Now, if we allow seasonality, I think you mentioned seasonality squared in your example or in your script. Is that right? This plane then converts from a flat plane to more of a surface that has a parabolic shape. So it would have something like, now the graphics are getting a little too difficult to interpret. But anyway, that flat plane allows it to become bendy. And so it can like have a parabolic shape along seasonality. If seasonality is discrete, then we're just going to have, let me go backwards. If seasonality is discrete into 4 seasons, we're going to have one of these graphs at each season. If we allow seasonality to be just categorical, but we're not doing things like seasonality squared, it's just seasonality. These are all going to have the same, let's see, they're all going to have the same slope. It's just they're going to be offset slightly on the intercept. The whole intercepts are either going to move down or up, depending on what that value of beta is for the seasonality for that particular season. So what it does is adds more dimensions to our graph here.
And this is all if seasonality was beta 2.
If we had seasonality was continuous times beta 2, so like 1, 2, 3, 4, and we treat those 1 through 4 as continuous numbers, and then they get multiplied by beta 2. That beta 2 is going to shift this whole thing either up or down. Well, if seasonality is continuous, then depending on how seasonality increases, the slope of the plane this way is going to either decrease or increase depending on what beta 2 is.
Okay.
Morgan, it looked like you had a question, but I think you just sneezed. Okay.
So Perry, I mean, we might get into this a little bit more, but wouldn't we basically be saying it, I guess why, thinking back to like 481 or 488, why wouldn't we just do like beta 2 times fall, beta 3 times winter? Or is that kind of what we're getting at the beta 2, but we're combining those? If they're continuous, then it would be 1x.
Yeah, good question. So, and how we would code that with our computers is, if we had fall, we would have all of our observations that occurred in fall would be a 1, right? And all the observations that didn't occur in fall would be a 0. So that model is J is which site we're at. Okay, log normal. We have an overall average, beta 0, or if we have categories, it represents a baseline category, plus beta 1 times flow, stream flow. We'll call X1 stream flow. Plus beta 2 times X2, and these have IJT on them. X2 is going to be, let's say, fall. And X2 equals 1 during the fall and 0 everywhere else. And then you have plus beta 3 times X3 IJT, where X3 equals winter. And 0 everywhere else, and so on. All through our, we're going to have 3 values of X's, because when X's are, we're going to have X2, X3, and X4. X4 will be spring. And then that gives us several combinations for our x's. So if we have x2, x3, x4, 0, 0, 0 is going to represent summer. 1, 0, 0 represents fall. 0, 1, 0 represents winter. And 0, 0, 1 represents spring. So this is binary coding that we can use to represent seasonality. And then stream flow is always going to be in there as long as stream flow is not 0. I'll finish reading this out. So we can work this out. Then we have during fall, the expected value is going to be beta 0 plus beta 1 times x1, and x1 is only 1 during fall, so we have beta 1. During winter, we have beta 0 plus beta 2. During spring, we have beta 0 plus beta 3. Did I do that right? Fall, winter, spring. And then during summer, all of our x's are zeros, so we just have beta 0. So when we're actually trying to calculate mu, our expected value, it's going to depend on the stream flow. Oh, I see what I did wrong. Okay. This should be beta 1 times stream flow. Plus beta 2. So stream flow is always in there. Beta 0 represents the average stream flow in summer, or the average nitrogen content in summer when stream flow equals 0, and then the average nitrogen content is going to increase or decrease based on stream flow depending on what we estimate beta to be. And then beta 4 is an offset, the difference in the intercept. The difference in the intercept for spring compared to summer. Beta 3 is the difference in the intercept in the expected nitrogen content in winter compared to summer. And beta 2 is the difference in the intercept in fall compared to summer. So all of this categorical coding deals with how do we actually interpret the output from categorical covariates. We have a baseline relationship for one season, and then we have parameters for the offset in that relationship for the other categories. Kelly, I think you had a question.
Just making sure that we I'm correct with that beta 2 is always interpreted as the difference relative to beta 3. Is beta 2 ever interpreted as the difference relative to beta 4? Or is it like a sequential?
Say that again.
Like when you were saying the difference in the intercepts, you were describing them sequentially, like beta 2 to beta 3 is the difference in intercept from fall to winter. Can you also look at it as beta 2 to beta 4 and the difference of fall to spring?
I think I see what you're saying. Yes, I mean the short answer is yes, but let's clarify that. So beta 2 is the difference in the intercept between fall and summer. And then beta 3 is the
Oh,
difference
yeah.
between the intercept between winter and summer.
Yeah, because
And we have
summer's
spring and
the
summer.
first one, so they're
Yeah,
all
summer's all zeros, so all of these get zeroed out, and that leaves just beta 0.
I have a question, and I think this is maybe about identifiability.
Mhm.
If beta 0 represents your intercept in the summer, if beta 2 equals 1, I mean, don't beta 2 or beta 3 or beta 4, they're all equal to 1. And the other ones 0 out because we set them to 0. So
Okay. So
this is-
beta
yeah.
2, beta 3, and beta 4 don't necessarily equal 0. It's the x's that equal 0. That's what we're choosing.
Oh, yeah. Okay, cool.
And we try and estimate what the betas are, and they can be anything, but they only get applied in here into the model when the x's equal 1. Otherwise, they get multiplied by 0 and they just get canceled out of the relation in determining what our expected value is.
Mhm. Okay.
So let me just, this is good review on understanding categorical effects, which is important not just for Bayesian statistics, but for all modeling. All right, so let's go back to our plot and think of our scenarios where we have our data. So we'll put in x1, x2, x3, and x4. This is stream flow. This is associated with fall, winter, and spring. And then we have our data Y here. So we go out to some sites, we collect some nitrogen samples. What are some reasonable values of nitrogen, Kelly?
really any real number, probably under 7 in this. So
Okay, let's say we go out and we collect a value of 8, and then 10, and then 200. Okay, and
I was thinking
in our,
nitrogen stream flow is probably going to be like 300 higher for these streams. It's going to vary between
okay.
like 20 and 300. Sorry.
No, that's right. That it was nitrogen. So now stream flow is so like 400, 500, and 600. The first sample we collected in the fall. So we put a 1 here and then a 0 everywhere else. The second sample we collected in the winter. So we put a 1 under the winter column and a 0 everywhere else. And the last sample we collected in the spring. Let me add one more for the summer. So 300 and then 700. And then these all get zeros for summer. So we collected it in the summer. We don't need 4 columns. We don't need 4 columns here for 4 categories. We only need 3 columns because binary combinations with 3 columns will give us 4 different distinctions because one can be all zeros. All right. So when we look at the first one, we plug all of this information here into our model. We're going to get, so for observation 1, we get beta 0 plus beta 1 times 400 plus beta 2 times 1 plus beta 3 times 0 plus beta 4 times 0. So this is going to be canceled out from our model. It's not going to affect mu because it's getting multiplied by 0. It's just going to be 0. We're going to have beta 0 plus whatever our estimate of beta 1 is times 400 plus beta 2. For our second observation, actually, I'm going to do our last observation. Beta 0 plus beta 1 times 700 plus beta 2 times 0 plus beta 3 times 0 plus beta 4 times 0. All of these are going to get canceled out. We're just going to have beta 0 as our baseline intercept. Here is stream flow. We're at 700 on stream flow. And then this is describing the relationship between mu and our x value. So if beta 1 is positive, this line looks like this. And mu is going to be, for the value of 700, is going to be right here. If stream flow was 350, halfway between, then our expected value would be here. All right, so that's for our first observation, but now let's look at what happens to our fourth observation. Let's look what happens to our first observation. Beta 1 is going to be the same for all of these, because we only get one estimate of beta 1. But here we have a beta 2. So what happens is the beta 2 gets added to beta 1, and beta 2 is the difference in the intercept between fall and summer. And that's the model we dealt with last time. So if beta 2 is negative by this amount, it's going to lower the intercept relative to what it was for summer. So this is summer, and then this is fall. We're going to have an overall lower relationship between expected stream flow and stream flow, expected nitrogen content and stream flow. We can rewrite this just to show it another way as beta 0 plus beta 2 plus beta 1 times x1, where x is our stream flow. And then this becomes our new intercept. So beta 2 is the difference in our intercept compared to summer. Now, the next step we're talking about today is how do we make it so in each group, these slopes aren't the same? And the way we do that is allow our beta 1, see here, and here, and here, to be different for each group, for each site. And we're going to do that just for stream flow. So we can put a J on that beta, indicating that that beta is going to be different at each site. All right, so let me take this, and then we'll go to the next step in finishing our model statement. our process model is not yet complete. Let's also allow the intercepts to vary here. All right, so anybody want to take a shot at finishing out this process model? We did this when we were talking about random or modeling our intercept, allowing our intercept to change for each group J. But now we're doing it both for J, for both our intercept and our slope. What do you think, Meredith?
I don't know. Yeah, I don't have any idea. Sorry.
All right, let's start with, let me get it started here. Does that help?
So we need to have hyperpriors for the betas.
We're gonna actually have parameters for the betas.
Okay. Yeah, we had okay, so you're saying like when we did our Bayesian hierarchical model for different intercepts,
Yeah,
we had a normal distribution of like a mu beta 0 j and then like a sigma squared beta 0 j.
yeah, and I'm gonna omit the J on this one because there was a point of confusion about that last time that we brought up. That they're not, these mu's and these sigma squares aren't actually changing. I just put this whole subscript down here to indicate it was with there. So I'll leave the J's off on this one. Yeah, that's right. And then we put parameters on mu beta 0. We said maybe this was normal. And then we had some hyperparameters for this. And then we had sigma squared beta 0, and we had hyperparameters, or we had a distribution with hyperparameters for this. And that's where we were. Let's see, we also had sigma squared, and that is this sigma squared up here. We have a prior distribution for that. And then last time that was let's see. Oh, we also had beta 1. This was from our last model. So this would be like a beta 2 to beta 4. And those came from a normal. And variance with hyperparameters. That was our model for last time when we were talking about the Bayesian hierarchical simple linear regression model. Now we're extending it to allow a change in slope for stream flow for each one. So there's one additional step we need here to extend this model to allow beta 1 to change for each site for stream flow.
Do we need a mu and a sigma for beta 1?
Yeah, we need this stuff for beta 1. So we need to do exactly what we did for our intercept with our slope. sorry. Now, right now I'm using vague vague hyperparameters. So, or I'm using parameters such that the distribution is vague for all of these values. In practice, we'd want to try and inform those a little more if we can. But I just want to make the distinction between what are hyperparameters, the values I'm actually giving numbers to, and what are parameters that we're trying to estimate.
Could you reiterate what I, J, and T are?
Yeah, let me write that down. So for the ith observation, at the jth site, during the tth time. Now this is a good point. Are there, at any site during any time, are there more than one observations of stream flow and nitrogen? Do you ever do it twice, or do you just go there and take one?
Let's just do one for this case for now.
Okay. So then we can actually get rid of the I here. But if it was the case, we went to a site and you had two people and each person independently measured nitrogen content, then we could include I like that. But if we only have one site, then we can remove the I's completely. And the rest are good. Okay. All right. So at each site, during each time, there's one observation collected. So we don't need that extra repeated measures. Okay. So now we have our model statement. What's the next step?
I guess stimulate data.
We could simulate data from this, yeah. We could do that as soon as we get the model statement down. We could simulate data. Before we do that, though, so just so we get it done before the end of class, let's take this model statement and write it into a joint distribution. And just for completeness, let me put in the prior distributions here. I'm going to reorganize the way I wrote these following the Berliner method of doing data model, process model, and prior model. So I'll keep all the process stuff together.
Hey, Perry and Kelly, I have a question about T. Um,
Yeah,
so our model statement includes um, letting the intercepts vary by season. So that's like part of our research question is how does nitrogen concentration vary between seasons? And you're collecting this data over many years. Um, so are we seeking a also define a trend across all of these years, or is our model statement not equipped to answer that question right now?
yeah, good question. There's two temporal scales for time. Right now we're dealing with more of the, actually it's probably both of them. T is probably, let's see. Yeah, that's a good point. So we have two temporal scales for time. We have seasons, and seasons happen within a year. So one thing we could do is have a categorical variables like we do for season and just treat T as the year. So the repeated observations every year. Right now, as you said, we're not interested, we wouldn't be able to examine a trend through the years. We would have to include something in our deterministic process model that gives us that flexibility. What we can do with our model now is look at how the expected nitrogen count changes from season to season. And in some ways, the T is redundant here. It sets us up for developing the next step. If we do want to incorporate a change through years. So in a lot of ways, we can simplify this. Because our T is now in terms of X covariates. We've kind of converted the T subscripts and taken that information on the time, which is just season right now, and coded that into our X's. So now X's are representing the seasonal time period. And we're treating every year as being the same. I think we actually, let me take that back. Yeah, no, this is perfectly fine to write it this way if we're just interested in the time period for seasons. I think this is a good place to go in terms of from where we left off last with random intercept models. But I feel like at some point, Kelly, you probably want to incorporate an annual component in here.
Yeah, I would, just especially because we had really horrible drought activity paired in 2015 in this time series where things probably dried out in a weird way. And we also had a crazy snow year in 2017. So eventually I would like to like kind of understand some of those extremeness, but I feel like for the class, I'm happy to leave it at this just because, yeah, it's all new.
Okay, let's talk about what we would do if we were to extend this model. And then when we write out the full conditional distribution, we'll focus on the simplified version of that. And then you can think about as an exercise, how would you write out our full conditional distributions for the time period if we had them? All right, right now we have now we need the i's back in. For observation I, in group J, that's what the i's were. All right, I'm going to allow you to start over fresh in your notes here. Y for observation I, this could be any time period, in at site J. So we have i's equal 1 to n are the observations at site J. J equals 1 to 7 because there's 7 sites. Each site is going to have a mean. And that mean is described by mu of J. And each of our observations at site J are going to have some spread that's described by sigma squared. Now the mean, the expected value of our nitrogen count at site J is going to equal an intercept for each site. Plus our relationship to stream flow at each site. I need an I here because stream flow can change. Okay. And then plus differences, additive differences for seasonality. There are a couple of ways people write covariates. Sometimes they use X's and sometimes they actually write out what the covariate is. I'm going to use X's. And then say X2 equals fall. Okay, so now we're back at kind of what we had originally. Graphically, this looks like So it's just going to be, in the summer, we have our different slope beta 0j and our different intercept beta 1j for each of our sites. But then when we add this component for seasonality, it's going to have an additive effect here that shifts this either up or down depending on if beta 2 is negative or positive. Here I have it as positive. So it's going to take this whole plot and shift it either up or down. And let's say beta 3, which is the covariate for winter, is negative. So this whole plot gets shifted down relative to summer. So this line here is the same as this line. And then this is beta 3, which is negative. It shifts the whole graph down a little bit. Okay, so this is the model we're fitting. Then I could draw the same thing for spring, and it would just be an offset. And everything else is the same that we drew over here. Okay, does that help address the time question and clarify a couple things? All right. This is the model we're going to work on, but now if we wanted to add a year component, we can do in the simplest case, we could say plus beta 5 year, where year is continuous and we either have an increasing or decreasing trend through time. If we think that trend might not be linear, we could do other simple things like beta 6 times year squared. Give us a polynomial or parabola for year. I think because this is a fairly simple extension, I'm going to take back what I said about just going in small gradual steps. And I kind of actually want to add this to our data to see if there's a year relationship.
That sounds great.
Okay. All right, let's write out the joint distribution of this model. We'll be careful with our subscripts. Okay. What are our parameters? We can always start out there. We know the joint includes given the data, or the posterior distribution of parameters given the data. So what do we have for parameters?
Beta 0J.
Beta 0J. Good. What else?
We need beta 1J, and then don't we need all the betas? So beta 1 through beta 5.
Would we include the hyperparameters in this too?
We can always leave the hyperparameters off here, and they're just implicit in there. Yeah, good question.
We'd probably throw beta 6 in there too.
Yep, beta 6, I missed that one. What else?
Is that, oh, sorry.
Sorry, I was just going to say sigma squared.
Yep. Sigma squared. Four more, I think.
Need the sigma squared beta 0. And
Yep.
beta 1.
Two more.
The muse.
Yep. Okay. This is proportional to, start off with our likelihood.
It's proportional to all the betas again, right?
Yep. Do I have beta 1 in there twice? Yeah, I do. Okay. What else?
The muse.
Not yet. The muse don't come in yet.
Sigma squared.
Sigma squared, yep. So when we're looking at this, yeah. We have, what we're drawing right now is this. So we know we need the sigma squared in there because that affects y. The kind of tricky part is that we have mu in here. So there's a tendency to write mu there instead of the betas. But when we have something that's deterministically linked to it, we write out the parameters that determine the function for mu. Does that part make sense? Whenever we have an equals here, we're going to use whatever's on the right-hand side of that equal sign as the parameters. And then because we have all these and we know it's deterministically linked, we don't need the Muse. So when we write our Metropolis Hastings sample, we're going to be sampling betas. And from those betas, we're going to be calculating Muse. So it's really the betas that are changing. And then we calculate mu from the betas. Okay. All right, so we have our likelihood down. Now, what's the next part in this? Let me go back to finishing up my rearranging I started here. So yeah, it's already done.
Is it the likelihood of the Muse and the sigmas?
The Muse, let's see, which Muse and sigmas?
The mu beta 0, mu beta 1.
That's going to be part of it. But what we're going to, so we did this. This is deterministic. We don't need to do that. Now we have to do this. And now we have to do this.
Beta 0j given mu beta 0
Right.
sigma
Yeah.
squared beta 0.
Yeah. So we have mu beta 0 given. No. Let's see. Say that again. I misheard you.
We're saying beta 0j given.
Yeah, that's right. Right. And then the next one is okay, so now we've done this. We don't need that because it's deterministic. We just did that. We just did that. So the last thing are our priors.
Hey, Perry,
Yeah.
why is beta 2 through beta 6, why are those considered the priors?
Those are parameters, and they have prior distributions on them. So they're not considered priors, but they have priors, right?
So I guess I should have said, why are they not process models as well?
Okay, yeah, good question. So when we write out this, when we're writing out this and this, they have these components to them. Mu beta 0, sigma squared beta 0, mu beta 1, and sigma squared beta 1. These we don't know. We're trying to estimate these. These are parameters themselves. So beta 0j and beta 1j are parameters, but so are mu beta 0 and sigma squared beta 0. We don't know what these are. So because we're estimating the parameters that go into the distribution for beta 0 and beta 1, we incorporate them in here. Now, the question was, why don't we do beta 2 given something here? And why are those not considered process models? Well, we're choosing the values that go into here. We're choosing hyperparameters for those. We know what those are. Whereas in this case, we don't know what these are. So we're putting 0 and 100 squared in here. We're telling it that's what we want based on our prior information. But here, we don't know what this is. We're going to estimate these.
That makes sense.
And that's kind of in the hierarchical model, it's we have our likelihood, but then we have our likelihood with unknown parameters. But then we have parameters that depend on other unknown parameters. In both cases, we have a parameter here that depends on other unknown parameters. And we can keep going that way. We have parameters that depend on unknown parameters, that depend on unknown parameters. And we can go, if we have good data, we can make this hierarchy huge. We have all these, we have data at the top. We have some prior information we include at the bottom. And then we kind of squeeze them together to figure out what our unknown parameters are in the middle. And some parameters can depend on other unknown parameters and so on. Until we get to some point where we say, okay, we know something about this. We'll put some prior information on it. And then it's out, it's not in the hierarchy anymore. We're telling it something we know about it. Okay, so to finish out this, we have our prior models we need. We have priors for beta 2, beta 3, beta 4, beta 5, beta 6, sigma squared, mu beta 0, mu beta 1, sigma squared beta 0, sigma squared beta 1. And that's it. What do we need to develop Metropolis Hastings samplers for? Beta 0J, beta 1J, and all of our priors. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. If we discretize this and broke them out and did each one of them individually, we would have 14 different Metropolis Hastings samplers we'd have to write. The good news is these are essentially all the same. We can group those into one sampler using a block update. Probably want to separate these and these. And this. And so we're going to need 1, 2, 3, 4, 5, 6, 7, 8 different steps in our Metropolis Hastings step. We'll sample beta 0 using our MH step, then we'll treat that as fixed. We'll sample beta 1 in our MH step, we'll treat that as fixed in the next step, and go through all of our betas, sigma squared, and so on. Okay. Full conditional distributions. We have we need to write out 1, 2. Let's see, 1, 6. Here's what I'm going to do. Just going through the line on my screen. Okay, so we have to write out full conditional distributions for each one of these. I'll do these two. And can everybody else write out the full conditionals for where I wrote your name. We'll reconvene in about 5 minutes. And talk about these. Okay, is anybody ready?
I could be because mine are, I think, pretty repetitive.
Okay, let's do one of them then. We'll just do all betas. All right, go ahead.
Yeah. So this first part is probably the part that I'll mess up, where it's that proportionality sign, and I think it's just for J, not necessarily for I.
So you have your betas in here.
Mhm.
And within this whole thing, there's an I in here.
Oh yeah, but I just meant like I always forget the name of it, the tall, not summation sign. That's
Product
like
sign.
the product sign, yeah. So an I is needed for product sign too.
Yep.
Sweet. So yeah, then it's gonna be product sign I for I equals 1, n over I equals 1, and then product sign J equals 1, and then Yij is conditional on beta 0j, comma beta 0 or beta 1j, comma beta, or you can list them out, and then comma sigma squared, and then just the prior for whichever for beta if they're all blocked together.
Yeah, right. Okay, good. And these product signs, where they end up showing in our algorithms that because this is going to be log normal, we're going to have to sum all of those log normals that we calculate, because we're going to get one likelihood when we calculate DL norm for Y given mu or mu star. It's going to give us a whole list of I times J values. And then when we have to sum those DL norm values, and that's where the product sign comes in. So however many products we have to take, that's how many values we should be summing in our Metropolis Hastings algorithm. So you can check that to see how many values you're summing when you actually write the algorithm out, and to see if it's 7 times, I don't know if you had 10 observations, it'd be 70, you'd be summing 70 values. All right, who wants to go next?
I can go.
Jay? Oh, go ahead, James.
Yeah, so mine's just sigma squared is conditional on everything else, which is proportional to the product of I and the product of J. And then you have Yij is conditional on beta 0J, beta 1J, all the betas, sigma squared times sigma squared.
Yep, good job. Okay, Brian, do you want to go now?
Sure. Yes, beta 0J. And I believe we just have the single product sign for J here.
So beta 0J is in here, so that means we're going to need this whole thing.
Okay, so then
And again, because
we
that
have
has that
Yij.
I. Yep.
Okay, so we'll need both of them again. And then, yeah, that same first term that is included in our other two. And then times mu beta 0 and sigma squared beta 0.
Okay. So you have, I'm going to tell you right now, there's something missing.
Okay.
But you have mu beta 0 and sigma squared beta 0. So when we're doing these, what we're going through is looking for, so you're doing beta 0J. What we're going through is looking for everything on this side of this equation that has beta 0J in it. So this has beta 0J, so we're going to include that. That means this has I and J, so we need both products. This has beta 0J, so this is what you missed here. And then you have, let's see, beta 0J. Oh, is that what you said?
No,
This is what you said.
yeah, that is what I said.
Okay, so none of these have beta 0J in it. So we're actually not going to include those.
Okay.
We're just looking for everything that has beta 0J in here. So this one, beta 0J is right here. So we need to include this. This one, beta 0J is right here. So we need to include that. And then we don't see beta 0J anymore. So no. Does that make sense, that process?
Yeah, it does. I think I got tripped up because we have mu beta 0 and sigma squared beta 0 on the right hand side of
Yeah.
Anyway,
Yeah.
yeah, it does make sense now.
It's easier than that. It's easier than that. It's just where's beta 0 and include those ones.
Cool.
So to finish this one off, we have beta 0J given mu beta 0, sigma squared beta 0. Okay. So let's follow up on that. That one, These two were the trickiest one. They're the ones that are have the hierarchy in it. All right, beta 1J is Morgan. Okay, let's do this one.
Oh, that's proportional to both of the product signs for I and J. And then the data given beta 0J, beta 1J, the rest of the betas, and sigma squared. And then beta 1J given mu beta 1 and sigma squared beta 1.
Yep. Okay. All right, what do we have left? Let's see, Mia and Meredith.
Yeah, I can go. I did sigma squared beta 0. Yeah, conditional and everything is proportional to, now I'm pretty sure that we don't need the I. I think it's just the J product symbol. And then it's beta 0J conditional on mu beta 0 and sigma squared beta 0. And then just the prior for sigma squared beta 0.
Good. Okay, Mia.
Okay, mu beta 0, conditional everything else, is proportional to the product of J, and then I think it's just beta 0J given mu beta 0, sigma squared beta 0 times mu beta 0.
Yep. Okay. And then we're done. I think we got them all, right? The two that I did were here. So there's 1, 2.
Hey Perry, you have beta 0s instead of beta 1s.
Oh, right.
I think.
Thank you. Yeah. Beta 1. Good catch. Beta 1, beta 1, beta 1. Okay. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 steps in our Metropolis Hastings sampler to write. And that's our next step. Write out Metropolis Hastings sampler for these. Now there's a couple things I want to point out here. We have in our full conditional distributions here, we have normal and normal. What do we know about a normal?
Conjugate, right?
It's conjugate. Yeah. If we wanted to, we could figure out what this actually is, either by looking on Wikipedia to figure out what those parameters are of those the new normal distributions. A normal times a normal is going to be normal. And we just have to do that A inverse B, A inverse trick to figure out the mean and the variance of that distribution. We can figure that out and use Gibbs sampling. So we don't have to do Metropolis Hastings. Similarly, we have normal and inverse gamma. That's also conjugate. Posterior distribution of a normal times inverse gamma is going to be inverse gamma. We could figure out what those parameters are. This one's not going to be conjugate because we have a log normal in there. So this distribution is log normal. And then this is normal. We could check in Wikipedia, looking at conjugate priors, and see if log normal and normal is listed there. Go to continuous distributions. I See lots of normals, multivariate normals, uniform, Pareto, Weibull, log normal. So log normal is listed here. It says log normal, same as the normal distribution after exponentiating the data, but it doesn't give us any idea of what those parameters are. It's kind of vague. So I'm looking right here. It's like the most vague entry in here. So we could look further into that and figure out exactly what those distributions are and what they mean by this. Or we can always do Metropolis Hastings. So we did Metropolis Hastings last time for this when we sampled it. We could just borrow that code we already created, modify it slightly for application and use that. The downside to that is it's going to be a little slower than if we worked out the actual posterior distribution, because we're going to have to reject about 60% of our samples instead of accepting 100% when we use Gibbs sampling. Okay. Again, here we have normal, inverse gamma. That's conjugate. This is normal. This is normal. That's conjugate. So what we'll do for the remaining part of class, I can address any questions that we have, and we can talk about that. But after that, what I want to do is start to set up a sampler, simulate some data, and then work this out. So with the remaining 15 minutes of class, I can get you started on that. And then for lab, for homework / lab over the weekend, work on finishing out the MCMC sampler for this. The hardest part will probably be simulating the data, because we have these different sites that we have to have different slopes and intercepts for. And the bookkeeping on that can be more challenging to program. All right, any questions about this in this process? If not, I'll get started on a script. Oh, nice. Okay, let's go back to this model here. Let's choose some parameter values. And I'm just going to sample some parameter values from their prior distributions. So we're going to have sigma 2 beta 0. Okay, R inverse gamma. So for sigma 2 beta 0, I got infinity. Okay, not a great start. Too big. And I'm going to set these as true parameters because I want to call them back later to make sure everything is working. We also have betas. How many were there? Betas?
6.
6. And they came from mean standard deviation of 100. All right, now we have beta zeros, and there are 7 groups, right? Beta 0. We have sigma squared. And now we need our covariate data.
Hey, Perry, can I ask you a question?
Yeah, go ahead.
I'm not understanding the beta dot zero dot truth, 7 mu dot beta 1 truth. And then,
Yeah, I made the same mistake when I wrote out the full conditional distributions. Thank you.
okay.
There we go. Does that clarify that?
Yeah.
Okay. It was the same error you pointed out to me earlier that I made.
Oh, right. Yeah.
All right, covariate data. We have year. So let's see. How many samples do we want? Let's set up our design a little bit. So you have how many years? We'll say
We have 20.
20 years. Okay. And then 7 sites. Okay. And then within a year, at each site, how many observations do you have? And it's probably going to be different for each site. So you should have probably a n sub j sub t, because each year, each site, you'll have different observations. But let's just keep everything as a balanced design now, because what that does is add additional coding complexity.
Yeah, I would say there's roughly about like 4 per year per site.
Okay. Yeah, so, and all right. So we have, I'll say capital N. Well, do I need that? This isn't. Site. Oh, let's use capital J for that. That's what we used in our notation. Oops.
There's no dot after the beta zero truth either. In beta zero truth equals.
Beta zero dot truth. Where's that, Mia?
Right in that line you were just on. It's mu dot beta zero dot truth. 33, sorry, line 33.
Thank you. Okay,
After the 0, you set it up, I think.
there we go.
Yeah.
Also, I think mu beta 1 dot truth, does that need to be in normal?
Yes. Copy and pasting is getting me in trouble. All right, so we need to repeat sites for each year. So we have site 1 for 20 years, site 2 for 20 years, site 3 for 20 years. But we also need, how many? Oh, you said there were about 4 observations. So we also need to add 4 observations in each one of these. And we just have to keep track of how we're creating our data here. I mean, this is much easier in real life data because you know exactly what site, what year, what replicate it is, but just coding this, you have to be a little careful. So we can try a couple of things. So now we have, let's see, that's not what I want. I want each equals n. We have 20 years of data. We have 4 observations per year. Times 20 should give us 80 observations for our first site. And then 4 observations per year. 20 of those gives us all of our observations for our second site. So in total, we have 560 observations. Is this right?
Looks good.
Okay. All right, 560 observations. Now year. We have within 1 year, we have 4 observations at each site. So it's going to be something like we're going to have to repeat 1 to 20 a bunch of times. How many times? We need at least 4 in there. And 7 in there, let's see. But what we're looking for is year one. So we have 4 observations at one site. So 1, 2, 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, all the way up to 20, 20, 20, 20. And then that for that whole sequence to repeat for the second site. I don't think this will do it, but let's take a look. Not quite right. We have 1, 2, 1, 1, 1, 1. This should be 2, 2, 2, 2. So how can we do that? We have 2 minutes left. I'll try and get this done. I think this will do it. No. There it is. So first 4 observations at site 1 in year 1. First 4 observations at site 1 in year 2. And then we go to first 4 observations at site 2 in year 1. Okay. So we can start to put our data together, our design together. We'll have an observation number for each site for each year. Oh, not N. This is N. This is J. Here we go. Okay, that's right. Okay. Here's what our data look like. We have at site 1 in year 1, we have 4 observations. Site 1 in year 2, we have 4 observations. Site 1, year 3, all the way up to 20. We have 4 observations. Then we have at site 2, same thing, right? So that's how we're going to structure our data. Now we just have to simulate some values for that. So to do that, I'll create a design matrix. Let me do that here. Let's see, James has to run. I can do this in less than a minute. Okay, model.matrix, I call this X. We care about the site as a factor, it's categorical, plus year is continuous. Okay. Let me look at the dimensions of this, make sure it's correct. 560 by 8, which is exactly what we want to simulate our data. Okay. So from here, what I'm gonna do is I'm gonna finish this up, post some code, post the code online to simulate the data, and then the framework of the MCMC. And then for next week, let's say for Monday, see if you can write out the Metropolis Hastings algorithm for this and get it to converge. Okay, good. All right, I'll see you next week then.
Thank you so much.
Thank you.